Welcome back. So before we get into integrals that are defined in the complex numbers, um, I think it's going to be a good idea for you to revisit integrals in the real numbers. So recall back. So the thing you need to know is how integration is defined in the real numbers. So in single variable calculus, so calc 1, right? The way you would define an integral is a definite integral is if you have a function in between two x values, right? So if this is the function f of x in the real numbers, okay, I'm talking about the real numbers here. What we do to approximate the area that is under this curve here, right? What we do is we look at even line segments in between A and B. So we're going to look at what's called a partition. So if I define x0 as A and if I let xn equal B, I'm going to divide up this interval into even sub-intervals. So this will have x1 and then x2. And these dots means I'm going to keep going up to x sub k and then up to, oops, let me do a dotted line here. So down to x sub k plus 1. And I keep going, just taking down even slices of the subinterval starting from A to B. Okay, starting from A to B. And then what I'm going to do here is for each of these subintervals, I'm going to look at a point that is inside the subinterval. So if I look here, if I look at x of k star, I'm going to use this point to define as my height for a rectangle that is restricted along x sub k and x sub k plus 1. So this would be my rectangle here. And so what you'll see is an approximation of this area by using rectangles. So we'll have at 0 star here. So at 0 star here, and this will be another rectangle. Okay, another rectangle. All right, so and then to approximate that area, we just add up the areas of those rectangles, right? So the area would be just a sum. This is capital sigma, by the way. Let me do a define sigma here. So this is capital sigma. So what we're going to do is we're going to add up the areas of these rectangles. Well, the area of the rectangle is the width. These subintervals will have even length. So we'll call these delta x. So the width here would be delta x. So the width is delta x, but the height, well, it depends on each of the points that we pick inside the subintervals at sub k star. So in this case, the height of this rectangle is at f of x sub k star. So f of x sub k star times delta x. And then to figure out what delta x is, just take out the final minus the initial divided by the number of rectangles that you want. So A is the lowest point in the interval, B is the highest point, N is the number of rectangles. Okay. In your textbook, they use this definition in a general sense, right? This notation in the definition, this refers to the norm of the largest partition, right? Okay. But usually in calculus textbooks, they use an even partition. So this here would be a partition. Okay, so it's called the uniform partition. Nevertheless, right, this sum right here would be the approximate area under that curve, right? And then to get a better approximation, well, we can just take the limit of that sum as n goes to infinity, right? Okay, as n goes to infinity. And this is defined as the definite interval from a to b of f of x dx. And then by the fundamental theorem of calculus, hopefully you know this by now, the fundamental theorem of calculus would equal to this. This is a part 2 of the fundamental theorem. Capital F is the antiderivative of f, right? So where capital F prime of x is equal to little f of x, right? That's how it's defined. This is the fundamental theorem of calculus that you've seen here in previous courses. Okay, so it's good to visit that there. Also, there's going to be some new terminology that we need to go over. And this refers to this is referring to saying that complex numbers are vectors in 2D space, right? They're essentially vectors. So we need to revisit how to parameterize curves in two space, 2D space. Okay. So we're going to revisit on parameterizing curves here in a moment, but in the textbook, they refer to different types of curves and their conditions. So one of them is a curve that looks like this, let's say. So this curve is continuous and there's no gaps, right? So it's just a one long flowy curve from A to B. So they refer to this example as a smooth curve. Smooth, in other words, being continuous, and it's simple. Simple means you can break down this curve into smaller continuous curves. That's what it means. I'm sorry. Smooth is you can break down one curve into similar, smaller continuous curves. Simple means there's no intersections. Okay? There's no intersections. Right? No intersections. You could have a curve that looks like this. Right? So if I have a point A and if I end at point B here, and these curves are defined separately, right? So this example of a curve right here, this here is an example of a piecewise smooth, simple curve. Piecewise, you can break down this whole curve into separate curves. So in this case, we can break down this curve here into 3 separate curves. Smooth, this curve would be you can divide the curve into a uniform length. You can divide the curve into an even partitions, and it will be continuous. Each of those partitions will be continuous. Simple, there's no intersections, right? Simple means there's no intersections. If I have a curve that looks like this, on the other hand, where A equals B in this case, this here is what's called a closed, but it's not simple, right? Closed, but not simple. So this curve is closed since the starting point equals to the ending point. So in this case, A equals B. It's not simple because there is one intersection, right? So there's one intersection besides the endpoint, right? Besides the point where A equals B. So besides the point A equals B, there is one intersection, right? Closed means let me draw that again. So closed means there is another point of intersection besides the endpoints. Okay. And then the last curve I want to look at is a curve that may look like this. Okay. That looks like a circle or an ellipse in this case, right? This here is a closed and simple curve, right? Simple, there is no intersections besides the point where A equals B, right? In that case, we're dealing with a closed curve. Okay. So we're going to revisit these type of curves much late possibly in this section, but I know you're going to revisit those in the next section. We're going to deal with complex integrals. Okay, so let's see. I know I wrote some more notes about line integrals. Where was it? Okay. All right. Well, where is it? It's right here. Okay, so also in Calc 3, or possibly in calculus too, but I know that you've seen this in Calc 3, where you looked at integrals in a vector field in Calc 3. You looked at how to compute what's called a line integral. A line integral of a curve uh, defined in 2D with a function f of xy, right? I hope you have seen the definition of a line integral before, but if not, let's go over it just real quick. So here's the intuition behind line integrals. So if I look at a curve in 3 space, so I'm talking about the real numbers in this case. Suppose I have a surface that is defined by the function z equals f of xy, right? So this is a region whose region is created by taking points in the xy plane and you're plugging it into the z function. You'll get a z coordinate, right? So suppose I define a curve in the xy plane. So it could be a curve like this. Okay, so our starting point is at A and the ending point is at B. Okay, so what we want to do is we want to figure out the area that is within this sheet. Okay, so this sheet. So actually, let me color this in a little bit better. So we want to look at the area that's in this sheet right here. So this curtain. Right? So this curve right here, right? So essentially a line integral is you're looking at the surface area of this curtain, here, whose height of this curtain is defined by the function z equals f of xy. right? That's the point of a line integral. Okay, so if I look at a particular segment of this curtain, let's say here, right? So if I label this as et sub k and then or I should say et sub k plus 1 and et sub k here. So if I look at a particular segment of this curve, really what we have here is our height of this this rectangular segment. It will be defined by some other point et sub k star, right? Some other point et sub k star, and that is how we would determine the height. Okay, the et sub k plus 1 and et sub k points and et sub k star will be vectors. They will be points in the xy plane, right? So yeah, I want to make that clear. So et sub k plus 1, et sub k, and et sub k star will be points in the xy plane. Okay, so that's number one. And number two is we want to figure out the width of this curtain, right? And the width of this curtain, since we have a curved since we have since our curve since our segment is curved, I'll say that we are going to look at the width of this curve with respect to the arc length of this curve. So to figure out the width, we're going to have to use the arc length. So so the height, so let me list these out. So the height, this would equal to f of some et sub k star and then y sub k star. Okay. Right. And then the width. So the width of these curved rectangles. So if I look at et sub k, so this is the point, this is the segment in the xy plane. Et sub k plus 1. What we're going to do is, since our segment is not straight, okay, it has curvature. What we're going to have to do is we're going to have to approximate the length of this curve by using arc length. So it's time to get back to using the Pythagorean theorem. So if we draw in a right triangle, okay, so this length right here would be delta x. This would be the height, so this would be a delta y sub k, right? Delta y sub k. And the hypotenuse, just use use the Pythagorean theorem, right? So we'll have delta x squared plus delta y sub k squared, okay? And your heights will get smaller if we increase k, right? If we increase the number of subintervals, the delta y sub k star will eventually become delta y, right? So yeah, so we're going to use the width as arc length. So they labeled this as ds, little s, I'll say. And then, well, that's essentially what a line integral is. So a line integral, its notation is f of xy ds. Okay. All right, so the integral of the curve C, so we call this C here. That's how you figure out that's how you would notate a line integral. But in terms of a usual integral we've seen in Calc 1, this curve, we can parameterize this curve, right? So x and y, we can define those points in terms of a variable t. Okay, so so C, we can parameterize as x and y in terms of t. So x of t and then y of t. Okay. So that means the ds portion, we can rewrite this as delta x divided by delta t squared plus delta y sub k divided by delta t squared times delta t, right? So really this would equal to so this would equal to a sum, okay, equals 1 to n of f of x sub k star y sub k star times the square root of delta x divided by delta t squared plus delta y sub k divided by delta t squared times delta t. Okay, so that's arc length. If you want approximation, just take the limit as n goes to infinity of this guy, right? And I'm using that delta t will, this equals to b minus a over n. Okay, so that's the uniform partition that I'm referring to here. So in terms of t, the line integral, so the line integral, this is the part that you should write down, is the integral from a to b of f of x of t, y of t times the square root of x prime of t squared plus y prime of t squared dt. So in terms of t, this here is a line integral. Okay, a line integral. All right. So yeah, and then a couple more integrals to write down. If the x or the y of t is 0, you can write out the line integrals like this. So you may have an integral that looks like this, dx. Well, this equals to the integral of f of xt, y of t times x prime of t dt. And then if you have the line integral of the function with respect to y dy, this equals to the integral from a to b of f of x of t, y of t times y prime of t dt. Okay, so these are the line integrals that that are most important. Okay, so in this example, in this video, yeah, so this is just an overview of integrals in single variable calculus and line integrals in multivariable calculus. Okay, so we're going to see these a lot in the next video where we look at integrals in the complex variables. So let's look at some examples. You should be familiar on integrating these functions. So so integrate this function. And this one. So I'll call this integration review. So at this point, you should be able to work out these integrals. Okay. So pause the video and I want you to work on solving these integrals on your own. Okay. All right. I'm hoping you solve these integrals. Let's actually go over the solution. Okay, so part A here, we're going to look at a u substitution. So u equals 2x. And then if we differentiate both sides, du is equal to 2 times dx, right? So in terms of u's, the integral would transform to be the integral from 0 to pi over 4 of, in this case, 1/2 times secant squared of u du, right? What's secant squared of u's antiderivative? Should be tangent. I know you said that, so it'll be 1/2 times tangent of u, going from 0 to pi over 4. Okay, so this equals to 1/2 times tangent of pi over 4, which is 1, times 1/2 times tangent of 0, which is 0. So this is 1/2. All right, not bad. Okay. The other example, dx divided by x squared minus 6x plus 5. You're going to use partial fractions. Partial fractions decomposition. Okay, partial fractions decomposition. So the quantity that's in the integral, right? 1 over x squared minus 6x plus 5, right? You want to factor out the denominator as much as you can. So the denominator, it's factored out as x minus 5 and then x minus 1, right? X minus 5 times x minus 1. So the partial fractions decomposition looks like this, right? A over x minus 5, A over x minus 5, and then plus a capital B divided by x minus 1. X minus 1, right? Okay. Then you want to multiply both sides by the product of the denominators, right? So we want to multiply both sides by the product of the denominator, right? So we will multiply both sides by that quantity. So 1 is equal to a times x minus 1 plus b times x minus 5. Okay. All right. So the best way to look at this is plug in different values for x. So if x is 1, this equation becomes 1 equals to a times 1 minus 1, so that's 0, plus b times 1 minus 5, which is negative 4. So that means b is equal to negative 1/4. Okay. And if x equals 5, so if x equals 5, that equation becomes 1 equals a times 5 minus 1, which is 4, plus b times 5 minus 5, which is 0, right? So 1 equals 4a, which means that a is equal to positive 1/4. Okay. So that is the partial fractions decomposition, folks. Okay. So this integral right here, we can actually write this out as the following integral, the sum of integrals. The integral from 2 to 4 of, so 1/4 over x minus 5 dx minus 1/4 divided by x minus 1 dx. Okay. 2 to 4. Okay. And so this equals to 1/4 times the natural log of the absolute value of x minus 5. And then I'll have a minus 1/4 times the natural log of the absolute value of x minus 1. And this goes from 2 to 4. So this equals to 1/4 times the natural log of the absolute value of x minus 5 over x minus 1. Okay. And this goes from x equals 2 on up to x equals 4. So this is 1/4 times the natural log of, so the absolute value of -1 is a -1 over -3, so 1/3. And then minus ln of so 3/1. Okay. So yeah, so this is 1/4. It's 3. And that's, yeah, so that would be minus 1/2 ln 3. Right there. So we'll have a minus, so we'll have a -2 ln of 3. At minus 1/2 ln of 3. Okay. So hopefully that makes sense. And also I want to go over examples of some line intervals. So evaluate the following line intervals. So here's the first one. Let's look at this one first. So we want to evaluate the following line intervals. Here's the first one. So we have a line interval of y dx plus x dy. If C consists of the line segment from the origin on up to 0, 1, right? So this is 0, 1, and the origin's here. And the line segment from 0, 1 to 1, 1. So here and then here. Okay. So this will compose of two curves, C1, this line segment, and this other line segment here, which we'll call C2. Okay. So try to work this out on your own and see what you get. Okay, so you want to use the definition of the line integral that I gave out. So yeah, so you want to use the line integral here, right? Okay, so yeah, pause the video and see what you come up with. Okay, so I assume you worked out this example. Let's see what we have here. So I don't know if you noticed this, but this line integral x times dy, you can rewrite this as some function, some vector field f, right? Dot dr. Okay. So this is similar to what's called a work integral of a vector field, right? F dot dr, right? So this is the work done. of a vector field. So really, you're just calculating the circulation, right? And if it's 0, then that's what's called an irrotational vector field, right? So it's the same idea, right? So that's pretty, I think it's pretty important to point out. So in other words, so otherwise, we're going to look at how to parameterize the line segment. Or I should say the curve from 0, 0 to 0, 1, and then to 0, 1 is to 1, 1. So that curve will compose of two line segments, right? So the first curve C1 goes from the point 0, 1, 0, 0 to 0, 1, right? So what we have to do is parameterize this line segment. Now, back in past videos, we looked at this in the complex numbers. So really a parameterization of a line segment is x0 plus t times v, right? X0, so this is a point in 2D. And then v is the direction vector. Okay, to get the direction vector, you just take the final point where it ends minus the initial point where it starts. So x not the point, we can use this as the origin. And then v, the direction vector, this will be 0, 1 minus 0, 0. So we just subtract the points component wise. So the direction vector will be 0, 1, right? So the parameterization of this line segment, well, this will be 0, 0 plus t times the vector 0, 1, right? 0, 1. T is in between 0 and 1. That's the definition of the line segment. Okay. All right, so you can write this out as one vector. So 0t. Okay, 0t. The second curve goes from the point 0, 1 to 1, 1. And this is just another line segment, right? So we're going to use the definition of the parameterization of a line segment again. 0 to up to 1 for the range of t. So x naught is the initial point where it starts, so it's 0 to 1. The direction vector in this case is the final point, 1 minus the initial point. So 1 minus 0, and then 1 minus 1. So in this case, it's 1, 0. All right. So r of t, this equals to the point 0, 1 plus t times the vector v, 1, 0. So r of t, this equals to just one vector. So it'll be t1. And then, yeah, it doesn't hurt to check, right? So t is 0, we're at 0, 1. And if t is 1, we're at 1, 1. Okay, so this is, oh, shoot. So this is the parameterization of that other line segment. And then this line segment here too, right? So now we're ready to compute the line integral of the function y dx plus x dy. So another way to so y dx plus x dy. So another way to interpret this is so in terms of t, so if I look at C1, right? At C1, our limits for t is at 0 to 1. The y portion corresponds to y of t, right? So x of t here is 0, and then y of t is t. So y corresponds to y of t, so this would be t. Dx, this refers to x prime of t, but x of t is 0, So x prime of t is also 0. Okay, plus x of t, that will also be 0, right? Times dy dt. So y prime of t. Y of t is t, so y prime of t is 1 times dt. So that's 0. Okay? So that's how you compute the line integral of C1. So likewise, the line integral of C2 of, let me write this down right, y dx plus x dy. Well, this equals to the integral from 0 to 1. So let me rewrite the components here. So x of t is t, and then y of t is 1, right? Y, this is y of t, so this is 1 times dx dt. X prime of t is t, so so x prime of t is 1 plus x of t, which is t, times dy dt. Y of t is 1, so dy dt is 0. dt. Okay, dt. And so this equals to the integral from 0 to 1 of 1 times dt. So this equals to t, evaluated from 0 to 1. So this equals to 1. So the whole line integral of the function y dx plus x dy equals to, well, the line integral of C1 plus the line integral of C2, which is 0 plus 1, which is 1. Okay? Hopefully that made sense. One more example. Here's one more example. Evaluate. We're going to see this type of line integral, x squared plus y squared dx minus 2xy dy on this curve. Okay, so this is the curve C that we're talking about here, right? So this symbol right here, this indicates a line integral of a closed curve. So if you see an integral with a line integral with the circle in the middle, where the integral is referring to an integral of a closed curve. So in this case, C here is closed. And we're going to see an important theorem regarding to line integrals of closed curves called Green's theorem in the next video. So stay tuned for that. In the meantime, I want you to compute the line integral of this closed curve, right? We have x squared plus y squared dx minus 2xy dy on this curve. So pause the video and I want you to think about this for a minute or a few minutes. Okay, so I assumed you worked on this example. So this closed curve is going to compose of two semi-curves. I'll say that. The first curve is this line segment going from minus 2, 0 up to 2, 0. The other curve refers to this upper half circle, right, of radius 2. All right. So so this right here, this refers to the circle x squared plus y squared is 4. Okay. So let's actually compute the parameterizations of these curves. So for C1, this is a line segment. line segment from minus 2, 0 to 2, 0, okay? R of 2 is equal to the final point minus the initial point. So in this case, R of t would be a point, the starting point of the line segment, which I'll call minus 2, 0. So minus 2, 0 plus t times, so in this case, 4, 0. Okay, so in terms of a vector, we'll have minus 2 plus 4t and 0. So R of t is that. And t is in between 0 and 1. C2, on the other hand, C2, on the other hand, is the circle, the upper half circle of radius 2, right? So the parameterization of a circle, right? It was z naught plus r e to the it. That's how you do the parameterization in complex numbers. Right, it's going to be the same idea for real numbers. Okay, so it's going to be the same idea for real numbers. So C2, the parameterization of that curve. So R of t. The x coordinate would be 2 cosine t, and the y coordinate is 2 sine t, right? As the center is at the origin, right? And so the radius is 2, and this is the parameterization. T varies from 0 to pi, right? We're going to go counterclockwise. Counterclockwise. So that means the limits for t would be in between 0 and pi. Okay. So now we're going to do the integration. So in terms of the line segment, so the line integral of the line segment. So C1, so this is not a closed curve. So this is x squared plus y squared dx plus, or minus, excuse me. So this equals to 0 to 1, so that integral. So x of t is minus 2 plus 4t, and then y of t is 0. Okay, pretty straightforward. So x squared, that would be x of t squared. So that's minus 2 plus 4t squared plus y squared. So that's plus 0 squared times dx dt. So in this case, it's times 4. Times 4. Minus 2 times 0 times the x of t. So it'd be minus 2 plus 4t dt. Okay. So this will reduce down to so the integral from 0 to 1 of 4 minus 16t plus 16t squared dt, right? And so this so oh yeah, times 4. And so this integral should equal to 0 to 1 of 16 minus 64t plus 64t squared. Okay. And so by integration, so this equals to 16t minus 32t squared plus 64 thirds t cubed, which goes from 0 to 1. Yeah, okay, so from 0 to 1, um, yeah, so this would equal to, oh, what happened? Okay. Okay, so we're here. So this equals to, um, so this should equal to 16 thirds. All right, 16 thirds. Okay. Along the second curve now, so the line integral of C2, right? Uh, so I had x squared plus y squared dx minus 2xy dy as the line integral. Okay, so this equals 2. So this here is the x of t, and this is the y of t, right? Okay. And so this equals to the integral from 0 to pi of x squared plus y squared. So this is 4 times dx, which in this case is x prime of t. So we'll have minus 2 sine t dt um, minus 2 times x of t, which is 2 cosine t, times y of t, which is 2 sine t, times dy dt, which is 2 cosine t dt. Okay, and so if we simplify this, so this would be 0 to pi of minus 8 sine t. So we'll have a minus 16 uh, sine t cosine squared t dt. And I can simplify this even further. So I'll have a minus 8 times the integral from 0 to pi of sine t times, oops, that's not good. 1 minus 1 plus, excuse me, 2 times cosine squared t dt. All right. And then I can do a u substitution. If I let u equals cosine t, then du is equal to minus sine t dt. Pretty sweet. And so in terms of u's, we'll have 8 times the integral from, in this case, cosine of 0 is 1, and then minus 1's there. Cosine of pi is -1. So that's du, and we'll have 1 plus 2u squared du, right? Which is equal to minus 8 times the integral from -1 to 1 of 1 plus 2u squared du. 1 plus 2u squared is an even function. So we can actually write this out as minus 16 times the integral from 0 to 1 of 1 plus 2u squared du. And that equals to minus 16 times u plus 2/3 u cubed, going from 0 to 1. And this equals to minus 16 times 1 plus 2/3, which is minus 80 over 3. Okay? So, therefore, the line integral of the closed curve of that function will equal to the line integral of the C1 curve plus the line integral of the C2 curve. So that equals to, my goodness gracious, this equals to 16 thirds minus 80 thirds, which is negative 64 thirds. And that's how you do that line integral. Okay. So so that's a bit of review on integrals and line integrals, because it's going to get pretty intense in the next few videos. So before you do that, I want you to work on these problems, 1 through 10, and then 12, 14, 16, 24. That's good enough. Okay, so this is on page 243. Okay, 243. So for next time, we're going to be looking at complex integration. Okay, and I want you to keep these definitions and examples in mind because yeah, so we're going to get into pretty sweet content. So thank you for watching, and I will see you in the next video, folks.